Welcome back, everybody, after the coffee break. Now we jump from Trinidad and Tobago to Korea, as our next speaker is Byung-Jay Kahng. He got his bachelor from Seoul National University in Korea, summa cum laude, in 1990. I must admit that this is a remarkable university. I mean, going across the campus takes like 45 minutes. It's like a small city, a lovely place. But then BJ, I'm sorry, do I disturb you? Could you please start talking? Well, then he moved from Korea to California. And in 1997, he became my younger mathematical brother by doing his PhD under the supervision of Mark Riffel, our common mathematical father. And today he will, and now he is an American, and he works at Canisius University, where he is the chair of a mathematics department. So I think that that's as far as my introduction goes. And today, BJ is going to shoot far-reaching arrows at you. So even if you see the rear rows, these arrows can still reach you. These will be the magic arrows of Grupoids. And one more piece of information, which I forgot to mention, was that BJ is currently our senior science professor at IMPA. BJ, the floor is yours. Take it away.
Thank you. Thank you for the kind words. I'm certainly very much honored to be here and in this occasion. Now, over the years, I have had occasions to meet and know several Polish mathematicians, not just my academic big brother, Piotr Hayat, but for instance, Lech Peronowicz, whose papers led me into my learning quantum groups and other colleagues and friends. But also there was one other person as I was beginning my academic career. She was in probability theory, so not in my area, but she was really helpful as I begin the road, basically. So working with students and classroom things. And so along the way, I always was impressed by this breadth and then the talents of this Polish mathematicians. And I was wondering, and I know now, really, you have this wonderful program that they groom the next generation after next generation of the young mathematicians, and that way you keep the mathematical superpower status in the world. So, in that sense, I mean, please keep on and aim high, shoot arrows, and speaking of which, we wish to shoot arrows. So let's begin with one illustrated example. So consider some base points. And just for convenience purposes, I wrote 1, 2, 3, 4. But from a base point to another, we are allowed to shoot arrows, something like this. But there are rules. So you can, so you have this bunch of arrows, but if the 2 arrows who's like this one from 5 to 3 and then 3 to 2, if the target and source of 2 arrows match, then you can merge those arrows to make a new arrow. So for instance, 5 to 3, then 3 to 2 makes it into a 5-2 arrow. But on the other hand, if the target and source do not match, like the 5-3 arrow and 4-6 arrow, then you cannot merge, you cannot compose. So that's one rule. It's not like you have to have only one arrow from one point to the other, so you can have multiple of them, including that arrow from a point coming back to yourself. Could be scary, but still, I mean, that's allowed and many possibilities. But another thing is that for each arrow, you are allowed to come exactly back through that arrow. Then the effect of going forward and back or backward and forward, following exactly the same arrow, then the effect is that you're basically staying put, and you just they start from there again. So in some sense, that's like an identity. So that's the rule. And they trying to make that give a little bit more mathematical sense. The composition, sometimes called multiplication, would be, as we just noticed, they can, it's not all two pairs, the two arrows can be composed. So it's the multiplication or composition is only partially defined in that sense, in the sense that is target and source match. So a target of eta should match the source of gamma, so that you can put them together. Now, if you wish to call it multiplication, then you need another requirement. This is associativity. So if the composition would make sense, then where you put the parenthesis does not really matter. So that's the associativity, which we are pretty familiar with since we were little. And then we talked about the inverse, which would obviously flip the source and target. And as I was saying, if you send an arrow back or back first and then forward, then it essentially behaves like an identity in the sense as I described here. In other words, again, multiplication should make sense. So the gamma eta, if that makes sense, then eta, then gamma, and then back, then it's like just shooting only eta, and similarly from the other side. So it feels like multiplying one and not changing anything. So in that sense, that's an identity, but these are different. So you can see that there are lots of identities. So that's the main feature: partially defined multiplication, inverse, and lots of identities. And the groups that are special cases of Grupoids, which Grupoid, that name never came up now that I think about it. So we'll get to that. But groups are special cases of this arrow collection mechanism. So just to recall textbook definition. So the group has a multiplication satisfying associativity. But in this case, of course, multiplication is defined everywhere. And there's the identity element, and every element has an inverse. Now, what does this have to do with the arrows? And imagine that you have only one base point. So every arrow is shooting up and then coming back down. Then there is no worry about source and target matching, because there's only one base point, so everything will match. So in other words, multiplication will be defined everywhere. And identity, again, what we saw the previous page, multiple identities, that's not going to cause a problem because there's only one. So this is a special case group. And as we know from our classes and other research projects and things, the groups are important. Well, I mean, speaking to the math audience, and to say that groups are important, that's kind of silly, because it's kind of like eating well is good for your health kind of a thing. It's sort of obvious, but nonetheless, to make connection with what I want to say, I'll briefly mention a couple of occasions where groups are being used. Again, textbook level and not too complicated. So think about a square, 1, 2, 3, 4 square. And we learned that groups encode symmetry. So let's think about this one. If we only think about the corner points, then and allow shuffling, then that would give us a permutation group. But in this case, we have these sides to think about, so you cannot just deform the square. So the correct the group of symmetries should be what's called the dihedral group, which consists of 8 elements. Actually, the rotation, those. And then the reflection about the center horizontal line and reflection about the center vertical line, and then similarly for along the diagonal, the other diagonal. So that's what I had. There's actually one more reflection, about the exact center. But if you think about it, that reflection is actually none other than the 180-degree rotation. So there is no reason to list the same thing twice. So yes, something like this. And then if you want to do rotation and flip, and then it becomes the composition of these and things like that. So yeah, it is. You've seen these things. It's important and useful. And meanwhile, I mentioned fundamental group, and here again, the textbook examples. I have circle S1 and then sphere S2, and then fundamental group is then you start with a certain base point. Then from there, you think about homotopy equivalences of loops starting and ending at that point. And the homotopy equivalence is kind of like rubber band and stretching, tightening, and then see how that goes. If the rubber band is going only around here, then it's going to shrink down to one point. But if it goes around the circle, then you cannot really shrink it back. So that's different. And meanwhile, also you can go twice or 3 times. So you can shrink or tighten to deform things a little bit homotopy, but there's no way to make twice round a band to become 3 times once or something. So that's all different. So therefore, the fundamental group would be the integers. Oh, the minus number would be going rotating the other way. On the other hand, for the sphere, then even if you feel like you are bound the like equator, so the sphere, there is this other direction, so you can bring it over, and then everything actually comes down to shrink into one point. So therefore, the fundamental group will consist of only one point, and that kind of a thing is helpful because I mean, if these 2 objects were supposed to be same, homeomorphic, then the fundamental group should be also same, isomorphic, but they are not. So therefore, these 2 must be different, things like that. And the more complicated basis, you have the different fundamental groups and things. And you can go even further, like between R2 and R3. Yeah, I mean, of course, R3 is bigger, but still, can you prove? Well, because they go all the way. And so, the standard way to do this is if these were homeomorphic, then removing 1 point each should be also homeomorphic. And from R2, remove 1 point, then topologically speaking, it's essentially a circle. And similarly, R3, remove 1 point, is essentially a sphere. So something like that. So the groups are being used, I mean, in many other ways, but in particular, I mentioned these. So they useful. But then what about this Grupoid, which appeared in the name? And so here is the English, the dictionary definition of any kind of oid, suffix oid. Basically, what that means is that something like this, but not quite. So in other words, it's similar, but something is missing, or some things like this. So cardioid, and it looks like a heart, but not really the heart, and things like that. But then because of this name, it gives you a little bit pause. I mean, it might be something complicated or things like that. And that has been a little bit of a problem, and that happened to me too. I mean, the first time I learned of or heard of is probably the correct word. The Grupoids was when I was in graduate school, and from actually geometry the talks. And so at that time I was thinking, I mean, it's probably some kind of a special the gadget that geometry people use. Maybe I don't need that or something like that. It's just, just classic student mistake. And then several years later, I should have learned that at the time. And later I realized that I need to pick this up and things like that. So one of the aims of my doing this is to demystify this a little bit so that you don't do what I did. So what is a groupoid then? It's they imagine this collection of arrow thing that is what it is essentially, but to make things more formally correct, and it's a set where the multiplication is only partially defined, so you have to be composable, otherwise you cannot multiply. And but if you can multiply, then associativity holds, and they exist inverse, and here's the inverse property. So it's if A times B is possible, composable, then A inverse A, B is equal to B, and therefore A inverse times A behaves like an identity, and we notice that. But of course, you can do this not just with A, but you can do this with C inverse C and a whole bunch. So you think that there can be lots of those things that behave like identities. So we can, from the definition, we can define this set. So everything that is basically U times U is itself, so those guys. Then if you think a little bit about it, and anything that looks like A times A inverse is in there, because A inverse A inverse, then we could go back to the previous, then yeah, I mean, so maybe B inverse, then if you have A inverse, then essentially A inverse can be shrunk down to A and things like that. So you multiply twice, basically you come back to just once, and that's the U times U is U squared, the itself kind of a thing. And so in other words, everything that looks like A inverse or A inverse A are contained in there. But then you can also see that if you are an element in the G0 set, everything can be written in that form. So just write U inverse and U inverse assign according to this. So U and then U squared is itself. So it's so you can tell that that they are in there, and therefore you can define a map from the groupoid world to this set, to this G0 set, by doing either A inverse or A inverse A. So those are called a target map and source map. And the name basically explains what's happening. You start from A and then shoot A and then come back. Then you come back to the source. That's this one, and backward first and come back. And you are going to end up at the target of A. So those are on two maps, of course, and they behave like the identities, these elements we saw. So you call this identity space, unit space, or base. And when I was talking about the shooting arrows, I was saying that two arrows are composable when the target and source match. In the definition, that was not written, but that can be obtained as a consequence, like this. If you have here's the result. That is the source and target match. So in other words, A inverse, which is target. Oh yeah, so I should have written the other way. So source. So A, yeah, that's the source. And then that's B inverse, let's say. So that's the situation. Then you know, I know that A and A inverse can be multiplied. So you can put A there, which means you can put A there too, which shows that A and B are composable that way. And meanwhile, I mean, if you write it in this way, then this whole thing is A, so A, B. And so it's, I mean, you can make sense of A times B if the source and target behave in the way that you want. So again, that's not part of the definition, but it comes right away. Then also you go A, B, and then you can come back to inverse A, inverse, just like inverse of matrix multiplication. So you have those results. And so we know about the now Grupoids. Then what are the examples? We just saw that any group should be a Grupoid where the base consists of only one element. And then an interesting thing is that actually any equivalence relation is a Grupoid, which is interesting. So think of a set and then consider pairs, and we call X and Y pair. X and Y are equivalent if that pair is contained in, let's say, the subset R. But equivalence relations, so you need to have certain properties, reflexive, symmetric, transitive, things like that. And if you have a pair XY, then basically you think that the X is a target and then Y is a source. So if you're going to multiply, then the middle ones, the target should match. And then in that case, you multiply in this way. So X, Y, YW is equal to XW. That's how you would multiply. When I say pair Grupoid, then you don't even think about the subset equivalence relation. In that case, any pair is considered to be equivalent, and the multiplication from that way. Then this is an equivalence relation that I already mentioned. There was source and target, and unit space is essentially element in X. And then the fundamental Grupoid. So we talked about fundamental group earlier, but at that time we consider loops starting at ending at one same point, but you could allow multiple base points, and you could allow paths to go from one point to the other, or maybe it could be still a loop. So and then you'd be going into now Grupoid territory because of multiple base points. And then here's another important one in math. So a group acting on a space. Yeah, that's I guess the third the application of the group that appears most often. So this group has a symmetry, but here's the group action. And in this case, we can basically think that, I mean, I wrote the triples. So the X, G, Y, and that it has to be that group acting on Y should go to, it should be equal to X. So you think about only those triples, where the G is the group element, X, Y are elements from X, but not just any triple, but X and Y need to be related. And I just said related, and that was it's a kind of an equivalence relation. X and Y are related by G. If you have a group element that sends Y to X, then you can think that X and Y are related. So and thinking that the equivalence relation gives a Grupoid, then this would kind of make sense. And a source target, the source and target match, then you can multiply. And the group multiplication in the middle. Now, that's correct and everything. But on the other hand, if you think about it, that's a triple. But if you know two of them, then two, including one of them should be group element. But if you know two of them, then the other one is automatic. So in that sense, in actual applications, it's customary to just think about two elements only. So you can identify this Grupoid with G plus X. And you need to do a little bit of big bookkeeping. So if I know target and group, then the Y should be G inverse acting on X. But it's not really that hard. For understanding purposes, because it comes from the equivalence relation idea, that the first top formulation is easier to understand, but in application purposes, usually the second formulation is more used. Yeah, and we can do that. So I listed some examples, but why would anybody be interested in learning about
Sorry,
Grupoids?
may I request one more example? Can you go back to the previous slide, please? So here, this transformation groupoid makes sense for any action of G on X.
Yes.
But if you would assume that this action be free, then you can also define the Ehresmann groupoid.
Yes, free action is special. By the way, free action means, for those of you who are not completely familiar, then the group acts on an element, then the G on X, then if your group element is identity, then of course the X will stay put. But that's the only possible way. That kind of action is free action, and if you act on a non-identity group element, it moves elsewhere. But not all actions should be like that, I guess. So, well, yes, free actions.
So would you care to explain this Ehresmann groupoid of such a free action?
Well, I mean, I don't know. I mean, you mean the examples? Or?
Yeah. No, just in general, how it's defined. Because I think it's a beautiful example of a groupoid.
I don't know.
I mean, if you wish.
Yeah, and I mean, that would be the case where the basically the elements is going to, it's as if you're thinking of this equivalence relation, basically the elements will be hopping around, like moving the next one and next one, and things like that. And those, and then you could think about those orbits. That's also name in if you act on the elements, and then those related by group action, those will form a set called orbit that's kind of like the equivalence class, and then you have those, and then in that case, if it's well, I mean, it's I mean, what should I say? I mean, the understanding of the quotient space, I guess, they're coming from those collection of the equivalence classes. Is clearer, I guess. I don't know. I mean, what to say now. So it's I don't know exactly what you have in mind, but
all I had in mind is that when you have a free action, it makes sense to define it like this. You have a pair of points in your space X, and on this pair of points, you define an equivalence relation by acting diagonally with G on this pair of points. And the way why you can compose such pairs very much the same as you do it here is because the action is free. So there's always unique group element G that if two guys are in the same fiber, you can always make them identical by unique group element. And then you can multiply the third element by the same group element, and you have a well-defined composition for Grupoids.
So basically hopping around. So that's the feature.
And it's very important in principal bundles, and it also has a very important incarnation.
So that's what it might be. Yes. Okay. Yes. It's related to principal bundle. Yeah. Yes.
And it has very important incarnation in Hopf-Galois theory.
Okay.
Sorry, may I have a question? So if you are in this situation that you have a group acting on a set X, okay, you can consider this transformation groupoid, and then there is a construction of a C-star algebra associated with this groupoid. So this is one construction. But on the other hand, you can also take the so-called cross product of this continuous function on the space X and cross product with those G. So these two algebras are what? Morita equivalent or isomorphic, or?
Yes,
But yes, for what?
we're going
Or
there.
isomorphic?
Actually, that's later in the a few like 10 slides away or something like that. But yes, that's important. Yeah. So,
Yes, but my question is whether they are isomorphic or Morita equivalent.
I mean, for the if you just look we need to make sense of the groupoid algebra later, but that one and then cross product, those are actually isomorphic. But
Isomorphic.
but on the other hand, what's also what also can be considered is the space of orbits.
Yeah.
So in other words, X the mod by this equivalence relation. But then that one is not the same, but they are Morita equivalent.
No, but with the additional assumption that the action is very nice.
Oh yeah. I
Since
mean,
the
when
quotient
the
is
reaction,
is
yes,
Hausdorff. Yes,
proper, and yes, of course.
So the whole point is that if the action is not nice anymore, still this cross product makes sense, but this
Yes.
continuous function on the orbit space is just trivial. Yes.
Yes. So you're feeling my punchline down the road, but
Sorry.
that's actually an interesting feature that we want to look at. Yes, I promise to come back. So this Y groupoid, then we saw as examples that groups are special cases, equivalence relations are special cases, group actions are special cases. If you agree with me that these three are very important the tools in mathematics, then here is the framework that contains all these three things in one unified framework. So that must be useful. That's true. But on the other hand, that sounds like playing with words and being lazy. I mean, it's more philosophical than practical. So in that sense, I'll try to showcase a few examples where actually using groupoids seem to be more advantageous. I have something else in mind. So fundamental groupoid, I'll be pretty quick. But for instance, there are occasions where I want to describe this the topological space using fundamental group for the reason I mentioned earlier. But the space might be disconnected. Then instead of worrying about where should I put the base point here or there, well, just why don't we put both places and then think about this? And if you cannot find a path from one base point to the other, then you know automatically that they are in different components and things like that. So I mean, you can do a lot more than this kind of naive situation. But as I was saying, I mean, I have something else in mind. So let's move on. But this turns out to be useful. It's, like relaxing the definition of, but this one, let's spend.
Sorry, may I comment?
No, yes.
It's a very interesting point, which is related somehow to theorem which was used during some student talk. It was about the Van Kampen theorem. Yeah. So the point is that in this situation, if you want to compute the fundamental group of such cover or some decomposition of the space with this black parts which are disjoint, it is very hard to obtain this Van Kampen theorem. In terms of fundamental groupoids, it's very easy because the amalgamation of groupoids is very easy. It's even simpler than the amalgamation of groups. Okay, so this is the big advantage of groupoids over even groups.
Yes,
in the context of
I think that was the main point Ron Brown's textbook was making, and yes, it's in other words, use a little bit more kind of more generalized tool, which makes actually life easier if you learn the lingo. Now, the group is used as symmetry objects. So, but groupoid. Then let's think about this example. So this is a tiling, and a very simple one, not Penrose tiling, by the way. The horizontal vertical lines, the rectangles, and this for the and I want to think about the group of symmetry for this tiling. Then, of course, you can think about translations, but tiles should match the translations, and the reflections like reflect about any of these lines horizontally, vertically, or actually even things they're going through the middle of any of these things, or the center. So all the corner points, all the midpoints of the edges, and then center points, the reflection vertically, horizontally, those will work. No rotation here though, because this is no longer the square. If you allow, if you want to do rotation, that's only 180-degree rotation is allowed. So that's same as really reflection about the center point. So those will be the elements if you think about it. Yeah, so cool. So that's a lot. And a lot of elements, of course, means that it's it has lots of symmetry, which you can just see. I mean, it's pretty symmetric. The picture that we saw, that's what's happening. So that's true. But on the other hand, there's some things that give you a pause. Like I mentioned all this reflection, rotation, not rotation, the translation and things like that. That if we removed all these edges, basically only consider the vertices or lattice, I think that's a fancy name, then you would have ended up with the exact same the symmetry group. So, that's not necessarily a bad thing, and people often actually intentionally work with lattice to simplify things. But on the other hand, I mean, now they're tiling with the edges versus only the vertices. That's different, but the symmetry groups are different. So then that gives you a pause. And meanwhile, you just think about this kind of situation. So if somebody was tiling the floor, and then the quote unquote, I guess, accidentally, they put this tile in a flipped way, then nobody will notice that actually. In other words, that is a symmetry. I mean, if you just don't worry about the whole thing, just one tile, just flip it over, then it would be noticeable. In other words, a symmetry, but that's not in the list. So that kind of local symmetry is not being observed here. It looks like so. To emphasize more this kind of story, why don't we think about not the tiling of the whole plane, but some portion, which is actually more realistic to think about it. That the bathroom is finite, not infinity. So I made a mess of this, so I probably wish to raise things a little bit. But for instance, on something like this part, just this part, then think about the symmetry of elements that keep this finite portion. Translations are not allowed now. If you move this around, then you go way out. So all the translations are now out. And even for rotations, if you flip, not rotation, reflections, if you flip around here or something, then again, it goes out. So if you think about it, the only thing that's allowed would be, and think about this center, and then flipping vertical along the vertical line, the horizontal line, and staying put, and then the reflection about the center. That's it. So that's odd. In other words, only 4 elements indicating that there's not much symmetry going on here. But that doesn't seem right, because I mean you can just see that it's pretty symmetric. So what is the remedy? Actually bring in Grupoids, because group encoding the symmetry is useful for global picture. If you want to think about this local picture, then actually grupoids are more useful. And so here is the relevant grupoid that we want to consider. So again, think of this as an equivalence relation of some sort. So X and Y are related if there is a gamma, the group element, one of those translations and whatever the locations that we looked at earlier that relates them. And the operations look pretty familiar from the earlier situations. So I'm not going to, I don't need to elaborate too much on that, but just think about this thing. Then why is that more useful? Go back here, and then we'll go back to the earlier, the question of somebody accidentally flipping this tile over. That's now allowed. It's essentially saying that you can do this flipping reflection, but under this flipping, this right side and left side are equivalent. Basically, that's what this is. And I don't really care what happens to the other part, because so in other words, that particular grupoid element tells that for this tile, flipping is okay. Or if this tile happens to be colored, then here's another one that's colored. Then you can move, you can translate, and of course the other ones go elsewhere, whatever. So you may be worried about going out of this bound, but it doesn't matter because I'm not worried about the other ones. I just I'm only saying that this part and that part are equivalent under that particular translation and things like that. So in other words, by bringing in this grupoid the language, you can encode this local symmetry. So that's an improvement. So the name sounds like a more generalized group, but really, I mean, in many of these occasions, it looks like viewing it as a generalized equivalence relation seem useful. And what's happening is that typically what's happening often is that we say that two elements are equivalent and all that, but often what happens is that you sometimes forget how the equivalence was obtained. I mean, you shouldn't probably, but sometimes you only focus on the equivalent classes and things, but how you got there, or things like if group action relates X and Y, then maybe here's one group element relating these two, but there may be some other group elements relating these two or something like that. You may forget that if you focus only on the equivalence relation and equivalence classes, while if you use the grupoid language, then you actually keep track of all that. So it's not just these are related to these, are how they're related. That information is all contained, which is actually very helpful because as Adam noticed, again, we are not quite there yet, but we are gradually getting there. There are situations where a group acting on a the set space, let me say, because if it is just set theoretical, then usually those kind of complications do not really matter. But a lot of times you'd be interested in the set X having additional structure like geometry, topology structure. And after group action, then you would want to work with this set of orbits or set of equivalence classes. And by that time, depending on the actions, it may mess up the topology and it may look weird. And in that case, you be very hard pressed to study these things. But instead, by working with the grupoid, which actually captures all that and more, you actually can play with this instead of trying to work with this bad space. So to make sense of how to do that, we need a little bit more tools. So let's do that, which is a notion of convolution algebra. So at first, let's not worry about whatever topology, what I was mentioning. Just think about a groupoid and think about functions on the groupoid having finite support, which means that except at finite number of elements everywhere else, it's 0. And define the what's called convolution product between those the finite support functions in this way. And if you happen to know the convolution product from Fourier theory or something, then and it looks not quite the same or something, then I can fix that. It's ST is equal to P. So basically T is same as S inverse P. Then and then you let S move all the way, then it looks exactly like convolution that you're familiar with. But anyway, I mean, you can define a certain product like this at the function level, and I mean, to say that it's a product, then you need to have associativity things, which I won't do. But on the other hand, let me mention this special or example, or a simple example. To think about the set consists of n elements, 1, 2, 3, 4 to n, and think of the pair groupoids, the silly ones, just as any pair is considered equivalent to that one. Then convolution product should be A times B at ij should be such that that is summed over all possible composable pairs, so that you end up with ij. But in this case, it's a pair groupoid, so basically every ik and kj where the k's match in the middle. So that should be the convolution product. Instead of writing a parenthesis ik as a function, if I write it as a subscript ik, then I end up with expression that looks pretty familiar from linear algebra. So it says matrix multiplication. So what it's saying is that
you mean it's an UHF algebra?
Oh yes, finite dimensional. Yeah, or yeah, yes, yeah. I mean, yeah, in this case, yes. But yeah, of course. I mean, I usually get scared of the fancy words, but yes, that's true. Well, I mean, this is not a proof for associativity in any way, but at least this example shows that this probably would be, and it is true in general. And also along the way, I mean, I'm saying that the reach of the arrow world is pretty large. I mean, now matrix multiplication is under its the cover.
Sorry, I have 2 comments for this. The first one is that if you consider this construction for a group, you cannot obtain matrices. One can show this. This is the first comment. And the second one, maybe it is also worth mentioning that this is precisely the way in which matrices appeared in quantum mechanics, originally by Heisenberg in 1125, not in 1925, not in 1926, when the Schrödinger equation was discovered. So the Schrödinger equation was 1 year after, but the original approach by Heisenberg was exactly this construction, and he was led to this formula driven by experimental results. So it was very concrete stuff.
So in other words, what we now know as Heisenberg's matrix formulation did not start from matrices, but from this kind of thinking, and then he realized that there's a matrix going on in the back.
Yes, in some sense, he rediscovered matrices, but in fact, he didn't recognize it.
Oh, I see.
He didn't recognize it, but it was related to the fact that I think it's called, maybe Tomasz, you can comment, Rydberg formula, yes? Okay, that some frequencies add, but not all of them. So the frequencies were in this indexed by pair of elements, and only those pairs could be added where the second element of the pair was the same as the first of the second frequency. And the composition was like I pair ij composed with jk is the pair ik. So this is precisely this law. So of course the language of Grupoid was not present at that moment. In fact, as I said, Heisenberg didn't recognize the matrices at all, but the construction was very much in the spirit. So.
And please correct me if I'm wrong, but there's a book by Max Born, Matrix Mechanics, about quantum mechanics.
Probably you're right.
So yes, even 100 years ago, people they realized the importance of Grupoid. So, right. You now we can go further. I mean, just like probability theory, instead of thinking of just discrete situation, if you, in particular, if you have a infinite elements that like real lines or something, then we would want to consider topology on it and measure on it, and instead of working with this sum, try to think about it as an integral, just like what we do with discrete versus continuous random variables in probability theory. So we can make sense of all that if we can correctly make sense of what a topological groupoid should be. So it should be that the groupoid itself, and then the unit space, and then composable pair space. Those things should all have compatible, well, the topology, and then the maps multiplication and the source target map should be continuous. We have all that, then that's a topological groupoid. In particular, we would be interested in locally compact Hausdorff case, because in that case, it makes it's more convenient to make sense of the measures. So I say measures with plural, because the preferred way is not to give the measure for each of the target fiber. So in other words, think about all the groupoid elements having same target, and then for that fiber, give a measure, and then for the other collection corresponding to other target element, and the measure, and these measures should be compatible with each other, in particular, certain left invariance property. With that, then we can actually define the convolution product. There's this time functions that are compact, having compact support, but the formula looks pretty much the same as before. Instead of sum, now I have integral. So you can make sense of multiplication. Again, associativity needs to be proved, but that can be done. That's why we need it's a left invariance. Now, if I stay here, then that is an algebra with the product. But we heard a beautiful talk this morning about completion. So it's possible to give a good sense of norm for the situation, and you can complete this with respect to suitable norm, and that way you can actually obtain groupoid algebra, groupoid system algebra. So sometimes you may wish to work with measurable functions, or if you want, I guess, but you can actually get a system algebra out of this, which would be written as C star of the groupoid, which contains this convolution algebra consistent with compact support functions as dense subalgebra according to the norm. Now, these groupoid algebras carry lots of information. So and in particular, by doing so, now functional analysis can an analyst can come into play and then play with this toy, because this was as we just saw, I mean, it started likely as an algebraic object, and then the topologists and geometers got interested in it and then made use of them, and then through this convolution algebra business. Now the functional analysis the people come in. So it has really wide reach. These arrows go all over the place beyond the horizon. In particular, for my purposes, I wish to say something back to something about the situation of the transformation groups as a group acting on a space, but this time topological space. But sometimes the action may not be nice. So that so I'll give you an example soon, but not nice. So in the sense that the orbit space, the equivalence classes doesn't really have a nice topology to play with. So I mean, studying the space or functions in the space, is not too hard, but in that case, actually working with the Grupoid algebra that produce all these things, this as action, that can help to see that. So here is an example. So think about the circle, and then the group of integers acting on it by rotation. So rotate, 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 or it could be a big angle, then rotate, rotate, and keep on doing. Now that way you get the orbit. Yes, there are two possibilities. If the angle is nice, after a while you come back to where you started out with, then that forms an orbit, and then they start with another point elsewhere, and then do that another orbit which pretty much looks alike, and then collection of all orbits. You can form this the orbit space or Gaussian space. But then there is a situation where when the data is bad, like irrational rotation, then what happens is that here and then there and then there, and then you don't quite come there, and then basically you never really revisit where you were. So when you keep on going, and you end up with an orbit that's dense. And then what happens is that it becomes really complicated to distinguish between those points in the orbit and those not, because it's the orbit consists of dense points. So in other words, you cannot really break them apart, not Hausdorff. So the space of orbits is really bad. And then in that case, many of our the tools do not work.
Sorry, if I could comment. So in fact, this topology is trivial. So the only sets are the open sets, are the empty set and the whole space. And even from the point of view of measured theory, still L infinity, essentially bounded functions on this quotient is trivial. So this corresponds to the fact that this action is ergodic.
Yes,
so it is even worse.
Yes, it's a mess.
Sorry, I have to correct. The topology is not trivial. It's highly non-trivial. However, it is so strange topology that there are very few continuous functions. Okay.
Yes, so what I meant is that if we perform this usual construction, how the topology on the quotient space is constructed as a final topology, then this topology is trivial. But I agree, I would not say that this space itself is trivial. I would say that the classical understanding of topology leads something which is trivial. So in some sense, classical topology isn't helpful to understand this complicated space. Okay. The theory of continuous function on this topology is not enough to recover anything about the space, but the space still is non-trivial. Yes, for this I agree.
Yes, I concur. So and then that's kind of what I wanted to say too. But and then here is another way to visualize the situation instead of just going around this and the thinking that's going like this correspond to going around the torus and then slightly away corresponding to this angle. Then the good case would be kind of winding around and then coming back, and then the bad case you just go all the way, never touching, and then like this. So these correspond to the foliations of torus, and but in any case, as we heard from our our colleagues, there is a situation like this irrational rotation where the space is bad, and then making sense of the functions on the space is not really plausible, and therefore you cannot really deduce much information out of this. But instead, we would consider the groupoid coming from the action of this integer group on the circle, and they perform this groupoid, the convolution algebra and completion process. That one actually turns out to be a what's called cross product construction in cyst algebra. It's a pretty standard way to do things. So in other words, the groupoid cyst algebra is actually very much accessible. So we would instead work with this groupoid cyst algebra instead of directly with the orbit space. And you might argue that that's still not the same thing, is it? And things like that. And that's yes, but on the other hand, this is actually justifiable because, again, this appeared like 20 minutes ago, but in the good case, not just this example, in general, if the group action on the space is nice in a certain sense and proper action free, then there is a known the equivalence, what's called like Morita equivalence. But anyway, that the equivalence under a certain sense between the functions on the orbit space and the groupoid cyst algebra. So since that works at the nice case, you would think that even in bad case where one formulation is not really doable, replacing it with this groupoid cyst algebra language will still work, and then that way you can understand this logical property, and in this case foliation property, using this algebra language.
So would you agree that with groupoid cyst algebra for such an action of Z on the circle would give you exactly the rotational algebra Anna was talking about yesterday?
Yes.
Okay.
Yes.
Just to make a link.
Yes, exactly. Yes. Yesterday and also throughout the times we've heard about this Alencon non-commutative geometry where based on the Gelfand-Naimak, the picture of any commutative cyst algebra is essentially a continuous function that the compact or locally compact depending on. So, it's easier. Anyway, those functions on spaces, that kind of picture. So if we replace commutative cyst algebra to a non-commutative cyst algebra, it would be like studying functions on a quantum space, non-commutative space. Actually, the origin of that idea probably was this. This is where the Kahng already noticed that this bad, not really workable space, instead of pushing the issue there, try instead of study with the algebra, the corresponding algebra, then you can do things. And that idea led to non-commutative geometry, which later the branches out in many directions, including quantum groups and everything. So this is very again, the groupoids were playing the central role there. Then I thought about saying something about the groupoid and groupoid algebras coming from directed graphs, but probably considering the time, I wouldn't. But it's a very, very important topic. Peter can tell more about these things in some other occasion.
It's a beautiful application of groupoids.
Oh yes, this
Really.
is you even so yes, this yes. So thank you.
Thank you so much. All right. Any further questions or comments? Go
Yeah, I just wanted to mention that this groupoid associated with the irrational rotation, so in other words, the cross product, does lie in this class that is classifiable by this Elliott invariant that I mentioned.
Oh, great.
And in fact, every C-star algebra in that class can be described as a groupoid C-star algebra. This is a very deep result of Shin-Lee that's somewhat
Wonderful.
recent. So
Now, it's just the groupoid algebra. Do we need any kind of twisting or anything? Or
yes, maybe you might need a twist, but I'm not sure. I'd have to remember. But this gives a whole bunch of other examples of the appearance of groupoids.
Excellent. There's somebody at the back. Adam, could you please pass me?
I'm sorry if it was said, but I have a question. If groupoid has only one neutral element, is it a group, or is there an example when it's not?
oh, if there is only one base element, and then it has to be a group. So actually, there are some group of people, no pun intended, but anyway, I mean, thinking that actually groupoids should be called groups, and then the groups are some special kind of groups. So that way demystify this object, and because that sometimes turns people up, but they probably that's never going to happen.
Yeah, humanoid, yes. Adam, do you want to?
Yes, I would like to make one comment. So you mentioned those tilings, and in particular, you mentioned those Penrose tilings. So of course, those tilings are beautiful drawings, beautiful examples to show. But in fact, one could also describe it in purely, I don't know, combinatorial or more explicit terms. And for this Penrose tilings, you have two kinds of tiles, and the matching rules for those tiles are such that each Penrose tiling could be described by an infinite 0-1 sequence with some additional rule, but up to some equivalence relation. So it could be identified with this the Cantor set 0-1 to omega, divided by some equivalence relation. What is this equivalence relation? So two sequences are equivalent if they differ only at finitely many places, okay, finitely many entries. And so this is also some kind of quotient space. And in fact, this space is precisely this space if you think of these all possible sequences as a binary expansion of a real number from interval 0-1. This is precisely the space which is used to construct non-measurable sets. And in some sense, one could argue that the cardinality of this quotient space is in some sense greater than continuum. In ordinary set theory, in ordinary sense, it is continuum. There is a clear surjection from 0-1 to this space of Penrose tiling, but you cannot constructively define the section of this map. And in fact, it can be proven rigorously that you need an axiom of choice in order to construct the map going the other way around. So there is no constructive, explicit way to define the inverse mapping. So in some sense, and this is the typical feature of non-commutative spaces. Okay.
But what does it have to do with groupoids? I missed the point.
Maybe not with groupoids, but with this tilings and with this idea of taking a quotient. So
there is some groupoid behind this because it's presented in terms of some equivalence relations. Okay, every equivalence relation defines a groupoid.
Okay, in that sense. Okay, thank you. Yes. All right. Anybody else? Any further questions? I don't see anybody on Zoom with a raised hand. So let me end with the following question / comment. again on behalf of Tomek. Would you agree that, because it was somehow missing in your talk, would you agree that the simplest way to explain to someone, you know, a random person on the street, what a groupoid is just to say that it's a small category where every morphism is isomorphism?
I mean, I kind of intentionally were going away from that, although I heard a little bit about categories and things, but whenever I go there, then I tend to mess up. So I try to tread carefully. But yes, it's a small category, but unlike the typical categories, the picture, the arrow has backward arrow here, so it's so yeah, with the inverse, you said that, yeah, yes. So it's a special kind of that, I guess, but you know, it's true, and there are some the groupoid literature that focuses on that abstract aspects, but that's not my comfort zone, so I kind of went away from.
Okay, but I think it was important to mention because it's probably the most succinct definition.
Yes,
of a groupoid.
if you want a one-line definition of groupoids, I think what they do is groupoid is a small category with each element allowing inverse. I think.
Yeah, that's what I said. Yeah. Okay. Okay. So I think it's time to wrap it up. Let's thank our speaker again.
We wait for the main talk. Bye.
Great. Great debate. Fantastic.